Okay, well, thank you everybody for coming today to the DOE ARC seminar series. I appreciate everybody accommodating for the later time today. This was, of course, to accommodate for our speaker coming all the way from Australia, or joining us all the way from Australia. So, Chris, I appreciate you joining us here, given I know that the time difference is not very accommodating all the time. So. But today, our speaker, as I said, is Christopher Ferry from the University of Technology, Sydney. Chris is a associate professor at the University of Technology, Sydney, and the Center for Quantum Software and Information. His research interests include quantum learning and control. He obtained his PhD in applied mathematics from the Institute of Quantum Computing and the University of Waterloo in 2012. As many of us probably already know, Chris has a passion for communicating science and taking the most, I'd say, complex mathematical physics topics and turning them into lovable children's books. For example, as Quantum Physics for Babies and many other interesting books. So with that, I would like to welcome Chris, as he today is going to talk about quantum mean states are nicer than you think. Go ahead, Chris. The floor is yours.
Awesome. I still see your screen though. There we go. Okay. All right. All right. Thanks for that. Thanks for that introduction, Greg, and thanks for the invitation. And thanks for everyone for staying up late. As you know, it's tomorrow in Australia, and the world's still here. In case you want to know, the lottery numbers haven't been released yet, so I can't help you out there. And it's raining. There's a lot of rain. So I'm going to tell you about quantum mean states. So this is a talk about quantum states. And so I'm going to assume that you know a little bit about quantum states as we go through this talk, but we'll take it slowly. If you're going to just tune out, that's fine. I won't know because everyone's on mute and I can't see you. But I want you to take one thing away from this talk, and if this is the only thing you take away from it, then that, you know, I've achieved my goal. So what we've done is we've found a way to find the state that maximizes the average fidelity between a set of other states, and I hope that maybe you remember that, and also that it intrigues you a bit because it sounds quite simple. But we'll go through why that's not a trivial problem to solve. When I say we, of course, I don't mean the royal we. I mean a group of people. So myself. This map, I think, is useful for people in North America to remind them that other parts of the world exist. So this is the corrected map of the world. Putting Australia right dead center, a nice central location. So as Greg said, I'm Chris Ferry. I'm in Australia. This is joint work with Richard Kueng, who's in Austria, and of course, this is work that's done by a PhD student in my group, and that student is Afham. So Afham did most of this work through the bulk of the pandemic, not being able to travel to Australia. So we did most of this work all remotely, sort of decentralized and asynchronously, which is very incredible. Afham is now in Australia. So, but a lot of the work he had to do remotely, so I found it quite impressive. And you know, the results, of course, you know, are all obtained by him under Richard and I's supervision. So if at the end you want to know more about this work, then I'll put Afham's contact details in the well, I'll tell Greg to put it in the link in the description of the YouTube video, or he can send it out to you later, because we haven't actually submitted this work yet, so I can't give you a reference at the moment. But if you want to know more, if you think that what I'm going to tell you might be helpful to you, or you're interested in hearing more about it, then you have to just contact one of us, preferably Afham. Okay, cool. So what is this all about? So here's a picture of the space of quantum states, and I've put two quantum states there, rho and sigma. And one thing you might want to do with quantum states is measure the distance between them. Now, there's lots of ways to do this, and one of the most popular is the fidelity. So it's defined mathematically like this, and it's actually a kind of a really weird measure between states. If you're thinking about things classically, there's no classical analog. So like most things in quantum information theory have a very natural classical analog. And sometimes you just assume the states are diagonal, classical states, and everything reduces to some norm on vectors. And that's not the case with fidelity. But it is important because it actually can be derived from some geometric considerations. So it's a sort of related to the natural geometry of quantum states. And if you Google quantum geometry, you're probably not going to get the right information, just to let you know. So let me give you like an example. So here's the what this figure of merit looks like. It's not a norm in the technical sense. So if I say norm, that's just sort of an accident. So we have fidelity, which I just showed you. We'll have the Frobenius norm. So this is also called the two norm, or if we're talking about it being averaged, it's the mean squared error. And then we have the trace norm, it's sometimes called the one norm. And you can see that the Frobenius and the trace norm, or the two norm and the one norm, they're very, very similar. And fidelity looks very different. So what we're looking at here is the fidelity of every state in the block sphere, or say block circle, to the state that sits on the far right. Okay, is it right? I don't know. Is this flipping it? Is the blue on the right for you?
The blue's on the right. Yep.
Okay, I didn't know if the video was being flipped.
You know, left and right is the same on the southern and northern hemisphere.
Yes, indeed. So the state on the right is the one we're measuring the distance, or the figure of merit to. And of course, the state on the far left is the furthest away. So that's why it's yellow. And all the states in between have some different numerical value of the distance. So we go, interestingly enough, so fidelity is a number that's between 0 and 1, and 1 when the two states are the same. And so sometimes you'll hear people talk about infidelity instead, so it feels more like a distance. But in any case, obviously the states that are on the right are closer, and the states that are on the left are further away. But you see that this geometry, if this distance defines the geometry, then the fidelity is quite a bit different. Now, it starts to look a bit similar if you take a state that's in the interior of the block sphere. So now we're looking at a state that's moved inside the sphere a little bit, but you can still see that there's a stark difference between the fidelity and a typical distance that you might see. All right, and I want to kind of point out that the reason we focus on fidelity isn't because of some weird geometrical thing. It's actually probably the most important one as measured by what the community talks about. So you can see here's the last 2 weeks ago, the cover of Nature, or that was actually some work that I was involved in, trying to prove that you can create high fidelity quantum gates. And again, I've just used the word again, fidelity, right? So as a community, we've decided that fidelity is the most important metric that we're going to use. And so the problem that I'm going to tell you before we start working on this, that didn't have a solution, which should seem really surprising. Okay, so again, we're looking at the distance between two states. Now, the way I want you to think about this is in terms of there being like this true state. So in the pictures that I showed you before, I was although the gradient, the colors were like sigma. So sigma varies, and when we're trying to produce a state to solve a problem, the state is usually sigma, and there's this other state rho that is just fixed. So it's sort of like the true state. You can imagine if you were doing like some characterization, some quantum tomography, there's a real true state that you're trying to get at, and sigma are all the states you might consider as potential solutions. And we're going to generalize this a little bit. So now we're going to try to vary sigma in such a way that the distance, the average distance between a bunch of states that are fixed is minimized. Okay, so there we have, in this example, there's 3 states, and we want to find the state, oh, some feedback. We want to find the state that minimizes the average distance between these states. Now, when you look at this like geometrically, if you think, I mean, this is just a circle with 3 points and another dot. If you just think about this classically for a minute, you could probably intuit where that might be, right? Somehow the geometric mean between all of these states. And if I change the geometry a bit, I would still have some sense of it being the mean of these other states. Okay, so that this equation is somewhat trivial to solve, right? If there's one state and I'm trying to maximize the fidelity or minimize the distance to that state, clearly I just choose that state. So we generalize this to in the previous example, there was n equals 3. So now I want to minimize the average distance or maximize the average fidelity of this one chosen state that I'm looking for, sigma to a set of states I've labeled rho sub j. Okay. Let me just pause just to make sure that I've explained that correctly. So this is the entire problem. Find a state that maximizes the average fidelity to a set of states. So I hope that's clear. And we're just going to do one extra little generalization. Here you saw that there's a 1 over n. That's sort of our usual notion of taking the mean of a bunch of things, but those probabilities don't have to be all equal and be equal to 1 over n. They could be arbitrary. So now we have this set of probabilities p sub j which go inside the sum. So maybe you recognize this as the mean of some function, right? So now this object is the mean of the fidelity over this set of states. And again, those set of states will be fixed and given, and we want to solve essentially for sigma. So let's do a little test. Well, we know what the answer was for one state, right? If you have one state, then you just choose that state. That's clear. That will maximize the fidelity. So what if you have 2 states? I should have done some interactive quiz. Does anybody want to be brave? Greg. Oh, he unmuted himself. Where's the answer?
Oh, I was gonna say if you want to do a poll, you can do a poll.
Oh, right. No, I don't want to tinker with technology I don't understand on the fly and then have it be recorded.
I have a guess. This is
okay.
Anders. So thinking about your initial plot, the contour plot, I would think that the sigma lives on a vertical line on even distance from
Right.
row
So
2 and row 1.
so this one.
Well, not necessarily. I think it could be anywhere, vertically,
Yeah.
up and down.
Oh, I see. Yeah. Okay. Yeah.
I
fair
don't know.
enough.
That's my guess.
Yeah. No, that's a good guess. Yeah. So this is like obviously I'm not going to ask the question if it had the most naive answer. So this is sort of the most naive thing you might think about, that certainly in Euclidean distance as drawn minimizes the average distance between these 2 points on the circle. I think everyone can agree on that. So there, those 2 lines are slightly longer than these 2 lines. But in fact, the correct answer is here. So this is the state that minimizes or maximizes the average fidelity, minimizes the sort of distance implied by fidelity between those 2 states. And again, yeah, if you look at the original plot and you think, oh, I'll start at one state and I'm going to move to the other state following, the slope, right? You'll see that I should go along the contour of the circle. So, and things get, I mean, in this case, it's very simple, because one of the state, or both, well, in this case, both of the states are pure, and so you have this sort of nice linear geometry. And if you know something about fidelity, that formula that I showed you before reduces to just the overlap between 2 pure states. So it becomes a linear problem. But as soon as any one of those states moves into the interior of the state space, then it becomes more challenging. So in fact, if all the states lie on the surface, if all the states are pure, and I'm just using a qubit, and not even a qubit, a rebit, a real bit, as my visual example. But we've solved the problem in general. So just I'll show you pictures of kind of like qubits, but keep in mind that what we've done is more general. But so if all the states are pure, then we know what the answer is. But as soon as any one of those states becomes mixed, or in fact not rank 1, then we don't know what the answer is. Okay. So again, this is sort of the problem that we're trying to solve. In general, you have a bunch of states. Some could be pure, some could be mixed. Where's this state that maximizes the average fidelity? And prior to our work, this wasn't something that had a known solution. So I want to show you like an example of where this might be important. So maybe you've seen like a plot like this. Say this is in fact so now I've switched over to infidelity because it's nicer to see things going to 0 on a log plot. So 0 lower to the bottom of the graph is better. It's more accurate. So you see lots of plots like this when you're talking about estimation or sensing or tomography or anything where you want to have small errors. You'll have some like input parameter, some resource on the x-axis, and on the y-axis you have your figure of merit. And you hope that as you put more resources in, the figure of merit goes down. So distance goes down, so as the number of measurements go up. So this is actual data from a simulation of a tomography experiment, where we're increasing the number of shots and then performing tomography and checking to see if the state was close to the original true state that generated the data. What's shown here is the maximum likelihood estimator. Okay, but this you'll see plots like this, but really what you're looking at will almost certainly not be just a single experiment or a single simulation at each of those values of measurement shots. You would hope that the person who generated that plot had done a whole bunch of different experiments with a set of random input states. And if you get someone who's thought about that for a little bit longer, then you probably see error bars on these plots. In this case, I've plotted the interquartile range. And so the original line was actually the average infidelity, right? So every time I do a simulation and I check to see if my produced state, my maximum likelihood estimator, is equal to the original true state, then I get a value of infidelity. And I put that, I record that in a table, and I keep doing that over and over again, maybe, 100 times, 1,000 times. And then I take the average of those values and I put a data point on the graph, and I move on to the next set of parameters. I think this much should be obvious to most people, but what people often don't give a lot of thought to is how those random states are chosen, and after those random states are chosen, the fact that you've implicitly defined the problem that I just mentioned. So if I run tomography experiments or simulations with a different set of input states, typically those will be chosen randomly. I now have a collection of states, and I want to find the one state that maximizes, or in this case, minimizes the average infidelity to that state. And why is that important? Because when you look at this, you can see that, okay, well, the maximum likelihood estimator is good. As I increase the number of measurements, the error goes down, but how good is it? Is it just pretty good, right? So is the actual optimal the thing that I wrote down before? Is it down here, or is it closer? Is it here, right? And so this is why this problem is important, because every time you've seen a plot like this, you have no idea if it's good or not, because you don't know how it could have been. And in fact, for this set of experiments, this is the solution. This red line is the best you could do. It solves that optimization problem. So now you can look at that and say, more than, hey, my maximum likelihood estimator is pretty good, you can say, wow, in fact, it really couldn't have got much better, right? The actual optimal average infidelity is, as we get further in these measurement shots, is right on top of it. Okay, so how do we do it? So the first thing is to make it a little bit more formal. So I have this average fidelity, and the problem I'm trying to solve is optimize this function that's defined to be this average fidelity, subject to a set of constraints that this state sigma needs to be a density matrix. Okay. Now the way that we thought about doing this, and then the way that Afham went and did it, was by phrasing this as a semi-definite program. So phrase it as a semi-definite program and use some of the machinery and of the techniques that are available within that paradigm, and that you can maybe attempt to use numerical techniques to address once it's phrased as a semi-definite program. Of course, you can buy software that solves semi-definite programs, but what Afham was able to do was come up with a couple efficient solutions. So there's two solutions. I won't tell you how they're derived. Take a screenshot now if you want to actually start using them, because as I said, we don't have anything posted to the archive yet. So you can either contact Afham or just use these formulas. So there's two solutions. So of course, as I said, you can just attempt to solve numerically the semi-definite program, but that would be computationally very expensive. So what Afham was able to do was find an iterative algorithm that is a numerical approximation. And when the archive paper is available, you'll see that it's a very good numerical approximation. So you take a guess. In fact, the guess is the state below, which I'll talk about in a second. You take a guess, and then you just apply these iterations. And it takes very few iterations to actually arrive at something that's within, I don't remember, 6 decimal places of the optimal answer. Of course, those iterations require calculations. What he was also able to show was that if you assume that sigma and all of the rows commute, which might be the case if your ensemble of states are very nearby. I mean, if they actually do commute, then this would be a pretty good approximation. And in tomography, as you do more and more measurements, in some sense, your ensemble of states that you would consider are actually quite close together and would be approximately commuting. And so this is just a formula. You just take those states, and it looks like an average. So it's the average of the square root of those states, and then you square it, and keep in mind that there's a proportional to. So at each time you calculate this, then you normalize it, because the calculation might not be a normalized state. So calculate these things, normalize it, and you'll produce a state that solves that optimization problem. All right, so that's it. And to remind you what we did, we showed you how to find the state that maximizes the average fidelity. So I think I'll end there since it's late in the evening for you, and you probably want to get to your dinner or drinks or whatever. And I'll take some questions.
All right, thank you, Chris. It's actually 4:30 over here, so it's not.
Oh, all right. So it's time for drinks.
It's time for drinks. Yes, that's right. So any questions for Chris?
Hello, can you hear me?
Yep.
Yes.
Hi, thanks for the nice talk. So was this average distance known in some other measures, like other than fidelity, like this distance you showed in the beginning?
Yeah, sure. So I can tell you that, let me put up a slide where I don't have the definitions, but so for the 2 norm, it is actually the mean of all of the states in the ensemble. So if you just take the actual naive mean, literally just add the states together as density matrices, proportional to their weights, then that will be the optimal state. And there's a set of measures called Bregman divergences. So this includes like relative entropy and 2 norm and things like that. And you can prove that for all of them, the mean is the optimal. And I should point out, as I mentioned at the beginning, fidelity doesn't have a classical analog, but the 2 norm does. It's just the same 2 norm for vectors. And the trace distance does as well. It's the same 1 norm as it would be for vectors, just the absolute. It would be the mean absolute difference. There isn't a closed form solution for trace distance either. So that'll be our next challenge, will be to try to do the same thing for trace distance. And the classical analog trace distance is something that people do consider, sometimes called the geometric mean. If you're talking about a single variable, so if I want to find you have a bunch of data and it's weighted, then the 2 norm corresponds to the mean. The trace distance corresponds to the median. So, if we solved it for trace distance, it would be kind of like a quantum median state. But fidelity is it's just a different beast altogether.
Right. Thanks. Yeah, I think trace distance would be useful too.
All right. I think
close to the fidelity.
I think Afham's in the audience. So you hear that, Afham? Get on it.
I didn't quite hear that. Sorry.
So I mean, by having if you have fidelity, then you already have a bound on the trace, right? So, or on the trace distance. So I guess do you necessarily have to have a notion of sort of mean trace if you can sort of bound it by the mean of your fidelity?
Sure. Yeah. So in this plot, let me bring up the plot. Okay. So here the motivation was like, originally the motivation was, can we just find the lower bound so we can, evaluate these potential estimates, and then Afham went and just solved the problem instead. So yeah, in some sense, originally we just wanted to find a lower bound, and that, you could plot the lower bound, and if it was close to the lower bound, then that's obviously good. But there's hope that, with these new techniques that we could actually solve it. Also, the other important point is that this solution would be useful if you're doing your tomography or your estimation in a Bayesian framework, where you naturally have sort of a set of states. So if I have, if my state of knowledge is, if I can represent that as an ensemble of states, which you typically would do if you're using some Monte Carlo technique, then you would just use you would need the exact, so a lower bound wouldn't be helpful. You would need the exact solution. So if I have some ensemble or some distribution, and the only way I can produce samples from it is with some Monte Carlo technique, I do that, I end up with a bunch of samples. Okay, but now what? I need to find some one state to produce as my answer. And typically in these Bayesian scenarios, you just use the mean of that ensemble. But as we've shown, the mean isn't the optimal. If you've decided that infidelity is what you want to measure success by, then you shouldn't use the mean. You should use this estimator that we've provided.
So I have a question, if I may. So you showed us the formula. Here is the answer. But why should I believe this formula? Can you prove that it actually maximizes this average fidelity?
This formula?
Yeah.
Yeah. So the bottom one is the exact solution if you assume that all the states commute. That's actually not that difficult to prove. The top one, so so I'll paraphrase how I understand it. Afham can correct me if I'm wrong. So you set up the semi-definite program. You go through the machinery of duality, and you come up with this complementary slackness condition. And if you stare at the complementary slackness condition, you have some inspiration. I don't know where that part came from. Maybe Afham can recommend some way to make that magic happen. You come up with this formula, and then of course, what you need to show next is that it actually converges, right? And so in that's probably for you, for your, in the context of your question, the most important part, which I haven't showed you, is a proof of convergence of this algorithm, and it does indeed converge.
But, well, I take your word for it, but how do you know it converges to a maximum? I mean, but once you're there, that must mean that if you perturb this state sigma in any way, then the fidelity decreases.
Yeah. So okay, yeah, that's right.
So I haven't seen any traces of that here.
No, of course not. I've only told you the answer.
Maybe you're holding it back until you get it published.
there's no deep secret in it. But I didn't want to show you a screen full of mathematical equations.
Oh, okay. Thank you.
Yeah. As I said, like it's just a matter of we haven't completed writing up the draft and submitted it to the archive. And if you want to see the proof, yeah, send an email to Afham. He'll send it to you.
Okay.
Okay, one more question, if that's okay.
Yep, go ahead.
So what's known about the state that minimizes the worst fidelity with the ensemble?
Okay, yeah, so that's that's an entirely different problem. So the answer, I don't even know if anyone's ever even thought about it. I can't even imagine what it would look like. Okay, but for the classical analogs of some things like two norm, relative entropy, there is, and if you have a particular finite ensemble of states, this minimax problem is what it's called, has a known solution, but for other figures of merit, it's not even known in the classical case. So in some previous work that I did, we tried to find the minimax solution for relative entropy, quantum relative entropy, and it's a horrendously difficult optimization problem. I'm not even sure where you would start on it, but that's also in worst case analysis, an important problem.
Thanks.
Any more questions for our speaker?
Too easy.
Too easy. All right, well, let's thank our speaker again. It's always hard virtually, but thank you again, Chris. And as I said, the talk will be available on YouTube. If you're interested in getting the link, just please message me. It takes a bit for it to get out because I have to go through some bureaucracy here, but nonetheless, it'll make its way to YouTube eventually. Thank you again, Chris. And one thing I do want to say is our next speaker will be Sophia Economo on April. Let me check again real quick. April 6th. So please join us again next time. All right. Thanks again, Chris.